Hello. In today's lecture, we're going to be going through some of the homework problems that were posted in previous lectures. Okay, so let's get started. Okay, so question 1 was to show that R3 with the defined addition and scalar multiplication is a vector space. So show that R3 with the addition and the scalar multiplication that I mentioned is a vector space. Okay, so let's first show that the addition operation satisfies that K-NE properties, the commutativity, associativity, neutral element, and inverse. Okay, so the first one is commutativity. So if we have x, y, z plus a, b, c, we should be able to swap these around. Okay, but let's show that first by applying the addition and then trying to split it back up again. So by definition, this is going to be x plus a, y plus b, z plus c in that order. Now this addition inside the tuple, that's the addition on the real numbers. We're going to assume that that is commutative, which means we can swap the ordering of that. So this will be a plus x, b plus y, c plus z. Now again, we can use the definition of addition on the vector space to separate this into two parts again. So this is going to be a, b, c, because of those are the first elements here, plus x, y, z, because those are the second elements here. Okay. And by doing so, we've shown that this is commutative. Okay, what about associative? So this means we have something like x, y, z plus, and then we've got brackets a, b, c plus, let's say u, v, w. Yeah, so for proving associativity, we want to take the brackets from the last two elements and then put it over the first two elements. Okay, in other words, we can shift the brackets around. Yeah, we can use the definition of addition to combine all of these. So this is going to be x plus, and then we have a plus u in brackets. And then we have y plus b plus v, and then z plus c plus w. Yeah, now this addition inside the tuple, again, that's from R, which means it's associative. So the inner brackets can be shifted around. So we can do that. So this becomes, and then in brackets, x plus a plus u, y plus b plus v, z plus c plus w. And now we can reverse this vector space addition to separate this out into the three parts again. So this is going to be in brackets x, y, z plus a, b, c plus u, v, w. Okay, which means that this operation is associative. Okay, what about the neutral element? Okay, so my claim is that the neutral element is the tuple of just zeros. Let's show that. So if I have an arbitrary x, y, z, so x, y, z plus 0, 0, 0, this is going to be x plus 0, y plus 0, z plus 0. Okay, but again, we're working with real numbers, so adding 0 doesn't change the number. So this is just going to be x, y, z. Okay, which means this tuple of just zeros, this must be our neutral element. Okay, also called the zero vector. Okay, and then finally, for this addition, we have the inverse. Okay, so if we're given x, y, z, my claim is that the inverse is minus x minus y minus z. Okay, we can show that that's the inverse by just adding these. So we have x minus x, y minus y, z minus z. And this gives us back our zero vector. Okay, which means that this must therefore be the inverse. Sorry. Okay, so that is our inverse element. Okay, then we have the adu part, the associative, distributive, then the other distributive, and unit. Okay, so let's go through those. Okay, so associativity with the scaling. Okay, so that's with our scalar multiplication. So if we have k times L times x, y, z. Yeah, so this k and L can go inside. Then we know that the real numbers are associative. So we can group the k and L together. So this becomes KL, x, y, z. Okay, so that's just using the scalar multiplication operation and the associativity of the underlying field. Okay, distributivity number 1. So if we have k plus L and then times x, y, z, okay, this is going to be k plus L times x, k plus L times y, k plus L times z. Okay, so that's just multiplying inside. But now within the tuple, those are just real numbers, we can multiply that out because we know that there's distributivity with the multiplication and addition of real numbers. So this is going to be kx plus kl, lx, ky plus ly, kz plus lz. Okay, and then finally, we can separate this out into two parts using the vector addition rule, and we can take out the k for the one part and the L for the other part using the scalar multiplication rule. So this is going to be k, and then we have xyz plus L, and then xyz. Okay, so that's just doing a few operations in one line. Yeah, but I'm sure you can see that there. Okay, for the next distributivity, that is if we have k and then two vectors, so let's say x, y, z plus a, b, c. Okay, so what we can do is add the vectors together. So we can put this as k, x plus a, y plus b, z plus c. We can multiply the k inside. So this is going to be k, x plus a, k, y plus b, and k, z plus c. Okay, then we can write this as kx plus ka, ky plus kb, kz plus kc. And then like we did before, we can separate this again. So the xyz part, we can take out separately from the abc part, and then the k we can also take out. So this can be written as k xyz plus k abc. Okay, so once we get everything into a single vector, we can just undo those operations using the scalar multiplication rule and the vector addition rule. And then we can manipulate it how we wish. Okay, lastly, the unit. So this is the unit from the underlying field. So if we have 1, in our case, is the unit, that's going, well, we're claiming the 1 is the unit. So 1 times xyz. Using scalar multiplication rule, that's going to be 1 times x, 1 times y, 1 times z. Yeah, but now all the elements inside there are just real numbers. 1 times x, that's just x. 1 times y is y. 1 times z is z. So we're left with x, y, z. Okay, but that is our original vector we started with, which means scaling by the unit from the field leaves the vector unchanged. Okay, so this is quite a long process, but it's important to understand the inner workings of these operations. Okay, let's have a look at question 2 and 3. So that was proving the uniqueness of the zero vector and the uniqueness of inverses. Okay, so question 2. Okay, show that the zero vector is unique. Okay, so a nice way to prove uniqueness is to assume that there's more than one and then show that they're equal. So if we assume we have 2, so let's say 0, 1 and 0, 2 are both zero vectors. Okay, then we can do a little bit of algebraic manipulation to show that they are then equal. Okay, so firstly, 0, 1 is equal to 0, 1 plus 0, 2, since 0, 2 is a zero vector. Okay, so what we did there was we added 0, 2 on the right-hand side, but since it's the zero vector, it doesn't change the vector. So we still have equality. Next, this is equal to 0, 2, since 0, 1 is a zero vector. Okay, so a similar argument. Instead of adding the zero vector like we did on the first line, we can also take away a zero vector without changing the value. Okay, because remember, if I have a plus the zero vector, that's just a. Okay, but now on the left-hand side, we have 0, 1. On the right-hand side, we have 0, 2, and they're equal. Therefore, the zero vector is unique. Okay, so this is a standard proof for proving uniqueness. You assume there's 2, show that they're equal, so there must only be 1. Okay, question 3. Show that the inverses are unique. Okay, so to show that the inverse of V is unique. Yeah, so how do we do that? Similar to before, we assume there's 2 of them and then show that they're equal. So let's say W1 and W2 are both inverses of V. So both W1 and W2 are inverses of V. Okay, so what does it mean to be an inverse? It means if you add it to the vector, you get back the zero vector. So we know that V plus W1 must be the zero vector, and V plus W2 must also be the zero vector, because they both are inverses of V. Okay, so now we write down something that's a bit, might seem a bit odd at first, but we'll see where it goes. So we're going to write W1 as W1 plus the zero vector. Now, we've already shown that the zero vector is unique, so this is perfectly fine. And we know that adding the zero vector doesn't do anything. Now, the interesting part is that the zero vector can be written in two ways. We can write it this first way, or we can write it the second way. They're both representations of the zero vector. So let's write it that second way. So we're going to write this as W1 plus, and then let's just put this in brackets, V plus W2. Okay, so I've just rewritten the zero vector using this other method. Okay, now we've got the brackets around the second two, the last two vectors there, but we know that this addition is associative, so we can shift the brackets to the first two vectors. So W1 plus V plus W2. Okay, so everything's fine with that. Now, W1 plus V, that's also the zero vector, using that first equation that's underlined. So this is the zero vector. But since we have the zero vector plus another vector, that the zero vector doesn't add anything to it, so this is just W2. But if you look at the left-hand side and the right-hand side, we see that W1 is now equal to W2. But we assumed two inverses, we showed that they were equal, so there must be one inverse. Good. So that means the inverse is unique. Okay, let's have a look at question 4 on subspaces. Okay, so we had a definition for a subset. So this was XYZ, such that X plus Y is equal to Z. Okay, and all of these are real numbers, so X, Y, Z are all real. Okay, so we've got the subset of R3, the subset of R3. We want to show that this is actually a subspace or vector subspace of R3 if we use the same addition and scalar multiplication that we were using before. So we need to show firstly that it's non-empty. We need to show that it's closed under addition and closed under scalar multiplication. Okay, so first, sorry, this pen's not working. Okay, so we want to show that this is a subspace first by showing that it's non-empty. So number one, consider the tuple 0, 0, 0. Okay, so in this case, X is 0, Y is 0, and Z is 0. Now, if we look at the condition to be in the subset, X plus Y must be Z. But in this case, we've got 0 plus 0 equals 0. That's perfectly fine, which means it satisfies the condition to be in the subset. So that means 0, 0, 0 is an element of W, which means W has at least one element. So W is not empty. Sorry, that is an empty set. Yeah, so W is non-empty. Number two, we need to show closure under addition. So if we take a W1, say W1 is given by X1, Y1, Z1, sorry, Y1, Z1. This is from W. And since it's from W, it must satisfy that rule to be in W. So we know that X1 plus Y1 must be Z1. That's from this rule over here. Okay, let's take a W2. So we can write this as X2, Y2, Z2. from W. And again, if it's from W, it must satisfy that rule. So we know that x2 plus y2 must be z2. Okay, so it must satisfy the rule to be in that subset. Let's add them and see what happens. So W1 plus W2 is given by x1, y1, z1 plus x2, y2, z2. But we know how to add these. The addition is inherited from R3. So this is going to be x1 plus x2, y1 plus y2, and z1 plus z2. Now, is this again in W? Well, let's just check the condition. The condition says the first element plus the second must be the third. So let's take the first element, add it to the second, and see if we get the third. So check. So the first element is x1 plus x2. The second element is y1 plus y2. Does this equal the third element? Well, let's see. We can rearrange this slightly. So x1 plus y1, we can put together. x2 plus y2, we can put those together. But now x1 plus y1, that is just z1 from this first equation. And x2 plus y2, that's z2 from the second equation. So this is in fact equal to z1 plus z2, which is indeed the third element. So yes, the addition of w1 plus w2 is again in W. Now we need to check the scalar multiplication. Is it closed under that? So let k be some real number, and let w be x, y, z from the subset W. Okay, so we need to check that the scalar multiplication of k with w gives us another vector in W. So kw, this is going to be k times x, y, z. We know the scalar multiplication rule. We can multiply it inside. So that's kx, ky, kz. And now we need to check, is this again an element in W? So check. So the first element plus the second element should give us back the third element. So kx plus ky. We can factor out the k. So we have kx plus y. But since this w was from the set W, it has that rule that the first element plus the second is the third. So x plus y in this case is going to be z. So this is kz, which is indeed the third element. So that's checked. Therefore, W is a subspace of R3. Okay. The next question was on proving that the span of a subset is a subspace. So let's have a look at that. So question 5. Okay, so prove that the span of, let's say, V1 to Vn is a subspace of V. Okay, so how do we prove that it's a subspace? We need to show that it's non-empty, closed under addition, closed under scalar multiplication. So, number 1, consider the following linear combination. So 0v1 plus 0v2. So this is indeed a linear combination. I've just chosen all of the coefficients to be 0, which is perfectly fine. So this is a linear combination. so it must belong to the span. Okay, but remember, 0 times a vector is the 0 vector, and the sum of a 0 vector with the 0 vector is just the 0 vector. So the left-hand side here is just the 0 vector. Okay, which means the 0 vector is an element of the span, which is good. We need that. And we've also shown that it is non-empty. So the span of V1 to Vn is non-empty. And it has the 0 vector, which is good as well. Okay, next we need to show that if I have one linear combination and another linear combination, if I add them together, I should get a third linear combination from the span. So number 2, let alpha 1 V1 plus alpha n Vn be an element of the span. Okay, so that's the first vector I'm choosing. And then I choose another one. So let's say beta 1 up to beta n. Okay, that's going to be an element of the span. Yeah, now I add them together, and I'm going to use my vector space properties. So alpha 1 V1 plus beta 1 V1. That's going to be alpha 1 plus beta 1 V1 using distributivity property. I can do that for all the terms up to alpha n plus beta n Vn. Okay, so I've got that. Now, alpha 1 plus beta 1, those are just real numbers. I can add them together to get another real number. Let's call that gamma 1. So gamma 1 V1 up to gamma n Vn. Okay, but this is just a linear combination. I've got my vectors V1 to Vn multiplied by some real number and then added together. So this is a linear combination. It must belong to the span. Okay, so I took two linear combinations, I added them together and got myself a third linear combination. So that means the span is closed under vector addition. Okay, number 3 is a closed under scalar multiplication. Let's see. Let alpha 1 V1 plus alpha n Vn be my chosen linear combination from the span. And let k be some scalar. Okay, so if I multiply k into this, I'm going to get k times alpha 1 V1 plus dot 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 up to alpha n Vn. But I can just distribute the k onto each coefficient. So this is going to be k alpha 1 V1 up to k alpha n Vn. Okay, now the k times alpha 1 I can write as some gamma 1, different to the previous gamma 1, but running out of letters. So that's going to be alpha 1 V1 plus dot dot dot, and then k times alpha n, let's call that gamma n. Now the gamma r's over there, those are just real numbers. So this is a linear combination. Since it's a linear combination, it must be an element of the span. Okay, so that means it's closed under scalar multiplication. So we've shown that it's non-empty, contains the 0 vector, closed under vector addition, closed under scalar multiplication, so it must be a vector subspace. So the span of V1 up to Vn is a vector subspace of V. Okay, So this is the standard procedure for showing something is a subspace. Okay, let's have a look at question 6, the last question for today. Okay, so this was proving that a given set is a basis for R3. Okay, so we've got the set 0, 1, 1, 1, 0, 1, 1, 1, 0. Okay, and the claim is that this is a basis for R3. Okay, so how do we show that something's a basis? First, it must be a generating set, and second, it must be a linearly independent generating set. Okay, so what does it mean for it to be a generating set? It means that if I pick any vector from the space, I should be able to write it as a linear combination of these vectors. So I should be able to write alpha 1, 0, 1, 1, plus alpha 2, 1, 0, 1, plus alpha 3, 1, 1, 1, 1, 0, for any x, y, z. So if you give me an x, y, z, I should be able to give you an alpha 1, alpha 2, alpha 3 that recovers the x, y, z. Okay, but this we can write as a system of equations because we have an equation for the first element, for the second, and then for the third. So we can write this as alpha 2 plus alpha 3 is equal to x. Then alpha 1 plus alpha 3 is equal to y. And lastly, we can write alpha 1 plus alpha 2 is equal to z. So by comparing each of the components, we can get one system of equations with 3 equations. This we can write as a matrix. So this is going to be 0, 1, 1 for the first column here, 1, 0, 1 for the second, and 1, 0, 0, 1, 1, 0 for the third. And then it's this times alpha 1, alpha 2, alpha 3. And that must be equal to x, y, z, which is given. Okay, and just something to notice, if you look at the columns of this matrix, that matches up with the vectors that are given to us. So the first vector was 0, 1, 1. The first column is 0, 1, 1. Okay, the second vector is 1, 0, 1. The second column is 1, 0, 1. And same thing for the third. Okay, so that's a general thing that you'll see. Now, we want to solve for alpha 1, alpha 2, alpha 3, given x, y, z. So that's the goal. So we want to solve for alpha 1, alpha 2, alpha 3, given x, y, z. Now, we can do that if the matrix is invertible. So if it's invertible, we can get a non-zero solution for alpha 1, 2, and 3. So this can be done if the matrix is invertible. Okay, and lastly, the matrix is invertible if the determinant is non-zero. So the matrix is invertible if the determinant is non-zero. If the determinant was 0, then we cannot find the inverse, and so we can't find non-zero alpha 1, 2, and 3. Okay, so we can just calculate the determinant of this. So the determinant of 0, 1, 1, 1, 0, 1, 1, 1, 0. Okay, you can check this. This is going to be 2, which is indeed non-zero. So we can find the solution to this. So in general, the alpha 1, alpha 2, alpha 3 values that we need are going to be found by taking the inverse. So 0, 1, 1, 1, 0, 1, 1, 1, 0. We found the inverse of this fixed matrix. We multiply it onto x, y, z, which is given to us, and that gives us the required alpha 1, alpha 2, alpha 3. Yeah. And that's how we find these coefficients. Okay, so we've shown that this set is a generating set because given any x, y, z, we can write it as a linear combination of those vectors. However, we might have more vectors than we need. In other words, it could be linearly dependent. Just a shortcut to that, we have 3, and the dimension of the space is 3. So this is actually enough, and not more than we need. But let's just show that anyway. Okay, so if we had 4, then that would be more than we need, because the dimension of the space is 3. If we had 4 of them, one of them could be written as a linear combination of the others. Okay, maybe I can leave that as extra homework. Okay, apart from the extra homework that is on the course webpage. Okay, so I uploaded that yesterday, so please have a look. Okay, so let's say we had, in addition to these vectors over here, we also included 1, 2, 3 as a vector. Show that this 1, 2, 3 can be written in terms of these other ones. In other words, find the alpha 1, alpha 2, and alpha 3. Okay, so if I add this to the set, it becomes dependent. Show explicitly by finding these alpha 1, 2, and 3. Okay, so that's just a little extra problem for you to do. Okay, let's get back to showing that these are linearly independent. So the way that we do that is we take these vectors and we write them as the rows of a matrix. Okay, so we're going to have 0, 1, 1, 1, 0, 1, 1, 1, 0. And we are going to perform row operations. Now, performing row operations is exactly the same, in this case, as performing those vector operations. So if I add 2 rows together, that's just vector addition, because the rows are the vectors. If I multiply a row by a number, that's just scalar multiplication, because the row is a vector. So we're doing exactly the same thing as vector operations. We're just organizing it a bit better. Okay, so with that out of the way, let's do that. We can move some rows around. We can do that because vector addition is commutative and associative and all of that. So we can shift the elements around. Okay, so we can have 1, 0, 1 at the top, 0, 1, 1, 1, 1, 0. Okay, then we can clear that last row of its first 1 there by subtracting the first row. So we're going to get 1, 0, 1, 0, 1, 1, 0, 1, minus 1. We can clear the second 1 in the last row by subtracting the second row. So 1, 0, 1, 0, 1, 1, 0. Sorry, so it's going to be 0, 0, minus 2. We can divide the last row by minus 2 to make it a 1. So we have 1, 0, 1, 0, 1, 1, 0, 0, 1. And finally, we can clear the last ones in row 1 and 2. So this can be written as 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. Now, since we've got it in this form, we know that these vectors must be linearly independent. If any of these rows were the 0 row, then it would be dependent. Okay, so this means the vectors are linearly independent. Okay, so just a note, if we had a row of zeros, then the system would be dependent. Okay, because that row that contained the zeros could be written as a linear combination of the other rows. Okay, so if we had a row of zeros, then the system or set is dependent. Okay, and then just one last note. So we took our original set of vectors, and through vector addition, scalar multiplication, and so on, we've got to a new set of vectors, 1, 0, 0, 0, 1, 0, 0, 1, 1. We call that the standard basis. So from one basis, we rearranged it into another basis, which we know is a basis. So this here, we know it's a basis. We call it the standard basis. So we call this the standard basis. Okay, but don't give too much importance to the standard basis. We can use any basis we like. Okay, so we have that choice of picking a basis. Okay, and you'll see more of that in the homework problems, the other homework problems on the course webpage. Okay, so please go through those. They're very important to look at. If you do have any questions, please just email me anytime, and you can visit me in my office. All the details are available on the course webpage. Okay, so later on this week, we'll be finishing off vectors, vector spaces, and linear maps by looking at eigenvalues and eigenvectors, diagonalization, functions of matrices, and finally, two important types of matrices, permission matrices and unitary matrices, which we will then see in the next chapter on quantum mechanics. Okay, so once this chapter is complete, we will have all the mathematics we need to look at the quantum mechanics. Okay, but please email me or come visit me if you have any questions at all. Okay, I'll see you next time.